Today, we're diving into a strange little character that's hiding inside the world of electronics, the Polaron. Now, this thing is kinda wild. It can be a hero in your solar panels, but a total villain in your phone screen. So, let's figure out what's going on with it.
Okay, so let's kick things off with a puzzle. We all know electrons are supposed to be the speed demons of the universe, right? So what's the deal when they get inside a material and suddenly act like they're wading through thick mud? The answer to that question is the Polaron, and it's the key to this whole story.
All right, to get to the bottom of this slow electron mystery, we kind of have to tweak our mental picture of what a solid material actually is. Turns out it's not quite as simple as we might imagine.
You know, we tend to picture a crystal as this perfectly ordered, rigid grid of atoms, like a beautifully paved superhighway, just waiting for an electron to zip right down it. But that picture, it's a little too perfect, and that's where our mystery really begins.
The reality is, that grid of atoms is much more like a wobbly, flexible net. The atoms are constantly jiggling around, vibrating, and it's this flexibility, this wobbliness, that holds the secret to the Polaron.
So how does this wobbly lattice explain our slow-moving electron? Well, it turns out the electron isn't just a passive traveler. It actually interacts with and changes the very structure it's moving through.
Picture this. Our electron has a negative charge, so as it travels through this lattice, it's going to push away other negative charges and pull the positive charges in closer. It basically acts like a tiny, moving magnet, warping the space around it.
And all of that pushing and pulling creates a little ripple, a distortion in the lattice that follows the electron around like its own personal shadow. In physics, we call this cloud of vibrations a phonon cloud. You can almost think of it as the electron creating its own little personal earthquake as it moves.
And this, right here, is where the Polaron is born. We stop thinking about the electron and its cloud of vibrations as two separate things. Instead, we treat them as one single entity, a quasi-particle called a polaron. So it's not a naked electron anymore, it's what we call a dressed electron, and it's wearing its own distortion like a big, heavy coat.
Now, this whole idea of a dressed electron isn't exactly brand new. It's been kicking around for a while. It really started back in 1933 with Lev Landau, who had this initial idea that an electron could literally trap itself. Then in the 40s, Solomon Pekar really fleshed it out and gave it the catchy name we use today, the Polaron.
Okay, but it gets even cooler, because not all polarons are created equal. They actually come in two main flavors, large and small.
So on one side, you've got the large polaron, sometimes called a Freilich polaron. And on the other, you have the small or Holstein polaron. The biggest difference between them really just comes down to how big and how intense that distortion cloud actually is.
The large polaron is kind of like a gentle, wide ripple in a pond. Its influence is spread out over a bunch of atoms, so the distortion is pretty weak. This means it can still glide through the material pretty smoothly, almost like a wave. You find these guys in materials like perovskites, and yeah, we'll definitely be coming back to those later.
The small polaron, though, that's a completely different story. Here, the electron's interaction is super strong, and it creates a really intense, localized distortion. This poor thing is basically stuck in a hole that it dug for itself, and the only way it can move is by hopping from one spot to the next. As you can imagine, that's a much, much slower way to get around.
So this dressed electron is heavier, it's slower, and you're probably thinking that's gotta be a bad thing, right? Well, yes and no. The polaron is a perfect example of a double-edged sword. Depending on the situation, it can be a huge problem or a brilliant solution.
The key idea to wrap your head around here is self-trapping. It's pretty wild. By distorting the lattice around itself, the electron literally digs its own little trap and gets stuck. It's like trying to run through deep, wet sand. The very act of moving creates the drag that slows you down. And this slide just lays out the two faces of the polaron perfectly. On the detrimental side, yeah, slowing down electrons is terrible for things like transistors that need to be lightning fast. But look at the beneficial side. That same distortion cloud that slows the electron down also acts like a shield, protecting it from getting lost or wasted. And that is a huge win for devices like solar cells. So let's pull this out of the physics lab and bring it into your pocket.
Because believe it or not, these polarons are working hard, for better and for worse, inside the gadgets you use every single day.
Take the next generation of solar panels, for example. Many of them are being made with these materials called perovskites. And their secret weapon? You guessed it, the polaron. That phonon cloud acts like a tiny bodyguard for the electron, giving it more time to be collected and turned into useful electricity. It's a classic case where being slow and steady actually wins the race.
But now let's flip the script and look at your phone screen or your OLED TV. In these amazing displays, the polaron is the villain of the story. It's actually one of the main reasons these screens eventually dim, wear out, and get that dreaded burn-in.
So here's what happens. In an OLED, light is created by these little packets of energy. Sometimes, one of these energy packets bumps into a polaron. But instead of making light, it just dumps all of its energy into the polaron, giving it this massive jolt. And this newly super-energized polaron can go on a rampage, breaking the chemical bonds of the molecules that make up your screen. Over time, that damage adds up, creating permanent dark spots.
So, it's pretty clear, right? The Polaron is way more than just some weird little curiosity that physicists talk about. It's a real-world player that engineers have to wrestle with every single day.
Honestly, the future of so many technologies, from clean energy to better displays, really depends on our ability to control these polarons. If we can figure out how to encourage them where they're helpful and get rid of them where they're not, we can unlock a whole new generation of amazing electronics.
It really makes you wonder, doesn't it? If we could become the absolute masters of the polaron, able to dial its effects up or down in any material we wanted, what kind of incredible new things could we build? The possibilities are just fascinating to think about.